Well, hello again. This is the fourth presentation in a series on the Collatz Conjecture. To reiterate here, we started with an introduction to describe the Collatz Conjecture and outline the steps in the proof. Following that, we had a lengthy series of 7 theorems that covered the main properties of the tree for the Collatz Conjecture. Then we mapped the odd integers in the Collatz conjecture into the signed integers in the Z domain, and we introduced the Z spiral representation of the tree that has a convenient structure that makes it easy to see how the Collatz conjecture converges to a root. And then here we're going to cover 4 more theorems to finalize the proof of the Collatz conjecture, and then we're going to give the conclusion. So, get down here to 4 more theorems. This is the last steps in the proof. So, theorem 8 is that every integer in Z that is odd and positive or even and negative will descend to a smaller integer in absolute value in a single iteration. We see this by inspection of the tables for the descent functions f sub d of Z. For the positive descent functions, all the descent functions for d greater than 1 have multiples that are 3 over 2 to the d, which is less than 1, so that the absolute value decreases. And for negative z descent functions, d less than minus 1, it's the same holds true. The multiplier is 3 over 2 to the d, and d is greater than 1, so that that's 3/4 or smaller, so therefore the absolute value also decreases. So that proves theorem 8. Spiral spoke decrements are the interesting part of the spiral. Basically, if you're decreasing or incrementing along the spiral cycle, you're not going to hit you're not changing the value very much. There are small changes. If you hit a spoke, then the change in the value changes by like a factor of 4 or something like that, since you go to an inner cycle or of some sort. This brings us to theorem 9, that every cycle C in the spiral has a magnitude C nodes, with 1/4 of the nodes being decrement spokes to cycles inside of C. In general, if you start counting a cycle starting with a starting positive Z value of Z0, then there will be 6 Z0 nodes on the cycle. 3 of those will be positive, 1.5 of them will be negative, and 1.5 of them will be spokes. The positive Z values are going to be Z0, Z0 plus 1, up to 4Z0 minus 1. The negative Z values are going to be negative Z0 over 2, negative Z0 over 2 minus 1, negative Z0 or negative 2Z0 plus 1. And then the spoke nodes are going to be 1.5 Z0 of those. The ratio of 6Z0 to 1.5 Z0 is 4:1. This ratio is also apparent just from inspection of the spiral that shows that every 4th node is a spoke. It's convenient to define 2 functions that make it easier to represent the descent function in the Z domain. Those 2 functions are the index of Z and the Z log of Z. So the index of Z is just the coordinate along the spiral, starting at 0 for node 1, and then incrementing by 1 for each value along the spiral. So for positive Z values, the index is going to be 2Z minus 2. For negative Z values, it's going to be negative 4Z minus 1. And of course, for the kth spoke, it's going to be 4K plus 1. So this is a convenient way to track the position of the Z value along the spiral. This also lets us define a Z log value, which is just the log to the base 4 of the index value, limiting it to 1, so that the root nodes at 1 and 0 both give a Z log value of 0. The z-log value is useful because since it's a logarithmic value, it changes more or less or very consistently across different octaves in the z-log descent sequence. So what's plotted here is an example of the descent sequence from starting value of z start of negative 18. That index value would be 71. So the z-log value starting would be about 3. And you can see that if you take the descent sequence that lasts for about 40 steps, initially it decreases down to about 2. And then it starts to steadily increase until it gets up to about 5. And then from there, it decreases rather quickly to get down to 0, which is where the root is. So this shows that the increments are rather slow since they're linear increments along the cycle, and then the decrements are rather fast because they're spoke decrements that tend to change a factor of 4 when you go down a spoke. This is another descent sequence. This is for a larger z start value of 2,718,281. I chose that value because it gives you a descent sequence that lasts for 50 clicks. So you can see initially it starts at an index value of 5,436,560, and that's up at the z-log value of about 11. And that decreases rather quickly till it gets down to around a z-log value of 3 or so. And then from 3 it starts to steadily increase till it gets up to 5. And then from there it decreases quickly, the same as it did in the previous chart. So it gets down to 0 by the time it gets out to click number 50. So this is another example of a z-log sequence. What we see here is that the decrements are rather fast since they change a lot when they go down to the spoke, whereas the increments are rather slow in comparison since they change linearly as you cycle around the cycles. This allows us to introduce theorem number 10. Along a spiral cycle, 1/3 of the nodes are reachable by descent from positive z nodes, and 1/3 of the nodes are reachable by descent from negative z nodes, and 1/3 are unreachable. This is easy to prove. The index value for positive z values is 2z minus 2. To that we add z's to get the next index value. So that gives us 3z minus 2, which is equal to 1 mod 3. So that says that 1/3 of the nodes are reachable by positive z values. The negative case works because the index is negative 4z minus 1. For negative z values, again, we add z to that to get the next index, which gives us an index of negative 3z minus 1. Z is negative, remember here, so that turns out to be a positive value, index value. But this is a mod or residue minus 1 mod 3. So that says 1/3 of the nodes are reachable from negative z nodes. The other 1/3 of the nodes are unreachable along a cycle. They can still be reached along a spoke, but not along the cycle. This brings us to theorem 11. For every step in the descent sequence, the probability of staying on a cycle is 3/4, and the probability of falling to a lower cycle along a red spoke is 1/4. This is easily seen just by inspection of the spiral, when you can see that 1/4 of the nodes are spokes that fall through to inner cycles. Some fall through more than one cycle, but they all fall through at least one cycle, and so the probability of hitting a spoke is 1/4. This makes it convenient to calculate the probability of hitting a spoke for consecutive steps in the descent sequence. If there's just one step, the probability of hitting a spoke is 1/4. If you take 2 steps, the probability of hitting a spoke is now 3/16, and the probability after 3 steps is going to be 9/64, and so forth. You can accumulate that. It's in the next column there. It's 0.25, 0.4375, and it steadily increases, getting closer and closer to 1. And the complement there is 1 minus the cumulative, and that's 3/4 for the for 1 step. For 2 steps is 0.5625. For 3 steps it's 0.41875. For 4 steps it's down around 1/3, and for 5 steps it's down around 1/4. The probabilities follow an obvious geometric sequence, which is 1/4 times 3/4 to the d minus 1 for d equals 1, 2, 3, and so forth. This sums up to unity 1. So you can tell then that the probability is going to steadily decrease. It'll decrease by 1 decade, or the complementary probability of staying on a cycle is going to decrease at a rate of 1 decade for every 8 iterations. We can extend this out to 100 steps on the decrement or the descent sequence in these charts here. That's on a log-log scale on the left and a semi-log scale on the right. The semi-log scale shows that the rate of decrement is 1 decade for 8 steps in the descent sequence. So if you take 100 steps somehow, then it's going to be a very, very small chance of not hitting a spoke. This lets us define a useful function called the delta z-log. The delta z-log is the change in the z-log value on consecutive descent values. So in this particular case, I've taken the statistics over some consecutive z values in the spiral. If the decrements are along the increments or decrements are along the cycle, which is what happens 3/4 of the time, then I tracked the mean and the minimum and the maximum plotted there. So the mean value in the change in the z-log is plus 0.04. The minimum will be negative 0.2, and the maximum will be positive, almost positive 0.3. If you hit a spoke, which was what happens 1/4 of the time, then the mean change on a spoke is negative 1.29, and the minimum is negative 8.9, and the maximum is negative 0.7. So you can see there's a difference between the maximum change on the spoke of negative 0.7 and the minimum change along a cycle, which is negative 0.2, which basically says the two distributions are separated. And so when you weight them together, according to 1/4 and 3/4 weighting, you get a net change in the mean value for the delta z-log of negative 0.29 per step. In other words, inevitably, as you step along the descent sequence, your average change in the z-log is going to be negative 0.3, and so you're going to hit the root inevitably, because you're going to hit the spokes that are going to inner cycles, and then your chances of decreasing increase accordingly. So that's the proof that you're going to descend to the root value at 0. This concludes the proof of the Collatz conjecture. What we've done is looked at the statistics for the z spiral to show that they converge to a root at z equals 0. Since the z domain represents all the integers in n that's congruent to 1 or 5 modulo 6, this means that the n values in n will also descend to an equivalent root node at n equal 1. The construction of the reverse simplified Collatz conjecture tree included all the odd integers in n. Theorem 4 showed that the odd integers that are multiples of 3, or congruent to 3 mod 6, will descend to an odd integer congruent to 1 or 5 modulo 6. So therefore, they also will inevitably converge to a root at n equal 1. The construction of the simplified Collatz conjecture tree showed that every even integer in n congruent to 0, 2, or 4 modulo 6 also will descend eventually to an odd integer after repeated divisions by 2, and therefore, as a consequence, they will also inevitably descend to a root node at n equal 1. So combining all of these results, we show that every integer in n will converge to a root node at n equal 1, and therefore the Collatz conjecture is true. This concludes the presentation, and it proves the Collatz conjecture is true. And then this is just some simple terminology that's summarized at the end. So thank you for your attention, and